Welcome to CDR Horizons, a new series from OpenAir hosted by Charles and myself, Harsh, in which we engage leading researchers about novel carbon removal technologies and ideas they're developing. CDR Horizons will explore the future of removing carbon dioxide and other greenhouse gases from the atmosphere, and we're excited to have you on this journey with us.
In this episode, we speak with Renaud de Richter and Wei Li. Wei is a senior lecturer at the University of Edinburgh, and Renaud is advisor to Methane Action. So today we go a little bit off the beaten path to focus on using solar chimneys for methane removal. And we discuss the trade-offs with methane mitigation and methane removal, and why methane is an important part of the greenhouse removal game. If you're interested in following more breaking carbon removal research, definitely like and subscribe to our channel for more content. And now, onto the show.
Hello, Harsh. Hello, Charles. Hello, everyone. My name is Wei Li. So I'm a senior lecturer in chemical engineering at University of Edinburgh, so here in Scotland. So I'm very glad that today, together with Dr. Renaud de Richter, we are delighted to share with you some of our thoughts and research on the topic of methane removal using solar updraft and photocatalysis or solar energy driven to help tackling global warming. So let me start with an ongoing project that I'm leading. So it is a research and innovation staff exchange grant funded by the European Commission. So the title of the project says it all. The title is Solar Updraft Power to Enable Atmospheric Photocatalysis for Non-CO2 Greenhouse Gases Removal and Emerging Negative Emission Technology. So the two images at the right-hand side here visualize the idea and the ambition. So let me explain this research a bit more. So first, I assume we are all on the same page about the emergency of global warming. So we can directly move to the importance of methane removal. So methane is a potent greenhouse gas, so nearly 30 times or over 80 times more potent than that of CO2, depends on how you compare them. So this figure here from the latest IPCC report gives the clear information. So at present, CO2 is the main cause of the greenhouse effect, about 0.75 degrees C global warming. So while methane is just the second, about half degree C global warming is caused by methane. So it is clear that methane is also a big player contributing to global warming. Another fact is that the majority of methane emissions, for example, from agriculture, landfills, wastewater sector, so they are all dilute and in concentrations lower than 2,500 ppm. Concentration of methane already in the atmosphere is even lower, just slightly below 2 ppm. So unfortunately, no mature technology is available to utilize or remove methane in these low concentrations. So there is a technology gap to deal with low concentration, but also you can imagine very large volume of gas or air. So why we think that solar chimney or solar updraft is one of the solutions. So let me show you how solar chimney involves. So it involves a very large greenhouse on the ground. used as a solar collector where the air is heated to create an artificial updraft. And a tall tower or chimney in the center of the greenhouse to build up the stack effect. So this idea was initially designed to produce electricity. You can install a turbine at the bottom of the chimney, so the huge airflow can drive the turbine to generate power. But from a chemical engineer's point of view, it can be a perfect gas phase reactor. It collects and processes large volume of air. So let's leave the power generation to a later stage and just at the moment, keep it simple for now to consider just the massive airflow it can drive. So, and apart from the this giant solar chimney, so there are other type of solar updraft devices. They all work in the same principle. So for example, ventilation chimney, chamber walls, and double skin facades. So they have a low footprint, so land footprint. Also, they can drive a large airflow and can be applied at even missing sources and at some hot point. So it seems that we have found half of the solution. So the other half, let's turn to photocatalysis. Photocatalysis starts from we call it photocatalyst material. It absorbs solar energy and converts the solar energy to chemical energy. The chemical energy can then drive chemical reactions. For example, with the help of this chemical energy, methane can react with oxygen and convert to CO2, so which is a much benigner greenhouse gas. So in an enclosed, very small container in the lab, so many reports has confirmed the photocatalytic conversion from methane to CO2 happens very effectively. And we already showed that solar updraft devices can drive massive airflow. So the real question is that whether and how this combination works. So our research tries to answer this question step by step. So let's first try something slightly larger than a very small container in the lab. So for example, we propose to install like 2 meters high solar updraft device together with for example, livestock buildings. So then one of the early questions is that can relatively low or moderate low solar radiation, for example, in most European countries, in this condition, solar radiation condition can we generate sufficient airflow, the updraft? So I think this is an important question because we will need to deploy the technology around the globe to have sufficient impact, not only in very good sunshine places. So we tested this idea, use both computer simulation and experiment on a 2 meter high device we built on our campus here in Edinburgh. So the results show that 120 watt per square meter solar radiation. This is relatively low. I will give you an idea later. So for this solar radiation, it is already enough to generate a considerable updraft, 100 cubic meter per hour per square meter. So this means solar updraft, it does not demand high solar radiation and can be deployed almost globally. So we also tested photocatalysis by adjusting the airflow passing through the device, so we can test photocatalytic removal of the 2 ppm methane in the air on the different reaction time, the residence time. So you can imagine with slower flow rate, we can give the air a longer residence time in the reactor, and the faster flow rates give you shorter residence time. So we measured a range of data, and from few seconds to nearly a minute. We also presented the same data in this table. So we can see 5 seconds rest time can achieve 20% methane removal, and 1/3 of removal under 10 seconds, half the removal under 15 seconds. So if we install a solar updraft device as high as a common livestock building, yeah, it can provide 15 seconds of residence time, so it can remove half of the methane passing through. And if we come to the giant, for example, 200 megawatt solar updraft tower, it can provide 10 minutes of residence time, more than enough to remove all methane passing through. So behind the data, so there are still some fundamentals need further understanding. For example, what are the limitations of mass transfer and diffusion of targeted gases, for example, methane, and the nature of the airflow we need to process. They are in large volume, low concentration of methane. So that means we need a large area of catalytic surfaces. And at the development side, we hope to keep our trajectory to upscale from small scale to cubic meter scale, or even to cubic kilometer scale. So also apply this technology in different scenarios. So we just want to emphasize that we already have a network, a consortium, and a knowledge pool. And also we have the plan, we have our initial facility. So we hope to attract enough further funding to support our research and keep it advancing. Yeah, thank you. Yes.
Great. So I think the one question we really like to start off with is like learning more about how, you got into this topic. What was your journey to this point? And what kind of got you interested in exploring this as something that would be of huge impact?
Okay, at my side, so as early as my PhD stage, my focus is photocatalysis. At that moment, not relevant to greenhouse gas removal yet. But at the point when I become an academic to start my independent research, so at a very fortunate opportunity, I get known with Renaud. So he introduced this, he pioneered this innovative idea, so to combine solar updraft together with photocatalysis. So at that time, I want to set up a photocatalysis research group, and with this very interesting idea, I decided to move directly into this direction. So why not? So that's the starting point. And then we set up a network and tried to put together a proposal for the European Commission funding. So again, quite fortunate we get a good starting point with the relatively small funding to start with, but a very good starting point.
That's exciting. Renaud, what about you? How did you get into this? And
in fact, we published a paper maybe in 2011 showing that by photocatalysis we can transform all the greenhouse gases, almost all of them. At that time, sulfur hexafluoride, we cannot do it, but we can do almost all of them, all the carbonated gases. And mainly it was in the gas phase. Some of them was on the aqueous phase, but that was only photocatalysis and was at the laboratory scale. And a couple of years later, I met somebody working on solar chimneys, and we wrote a book together. It was 21 renewable energy for the 21st century, which was quite new renewable energy devices using solar chimneys, for instance. And then the idea came that as the solar chimneys were the largest, the only structures on Earth which can drive the largest airflow passively, just by generating an artificial hot air flow. So we thought that it could be coupled. So we started publishing about this in 2015, about removing non-carbon dioxide greenhouse gases, especially methane, but also nitrous oxide, which is the third greenhouse gas, and many of the HCFCs, HFCs, and some CFCs. We find another people working in the solar chimney area in China, which is Professor Ming Seng, and we started cooperation, and that's how it started. And so we met Wei maybe 4 years ago, and all the team was constituted, all the consortium was done.
Oh, that's really exciting. I think what stands out to me is you were working on other renewable technology and like kind of source of technology and kind of found these parallels. And I feel like it makes me wonder, like, what are some of the other synergies between like sustainability fields that might exist and that people could be leveraging? But no, really cool. Thanks a lot for sharing.
Yeah, it's really cool how your paths all intersected
Yeah.
and kind of brought you into this research consortium and now here to CDR Horizons. I guess maybe to start off, so I'm curious about the solar chimney idea. So it seems like the land use for this must be very large, right? It has a very large footprint. What is some of the thinking around like siting, like environmental considerations, and also like, are there like opportunities here for dual use? If we cover this whole land with the solar chimney and all the mirrors, is there any opportunity to use it for something in addition to this kind of updraft, or any thoughts there?
In fact, the methane and other greenhouse gases are well mixed. And so in deserts, there is, of course, a solar chimney power plant has a very large footprint, but the land is very cheap in the deserts, and you can produce electricity in the deserts for poor people. And it's not a competitor with wind turbines or with photovoltaics or with CSP, because it doesn't use the same rare elements. It uses only cement, concrete, iron, and glass, and you can produce electricity with this. So, and also you have thermal energy storage underground during the day. And so they, with the prototype that was built in the 80s in Spain, they noticed that they still produce electricity after sunset for a couple of hours. And so they were investigating this, and they put some pockets of water bags on the ground, and they store energy during the day. So the daily production was reduced because they were storing energy, but then they produce a longer time after sunset. And some calculations have been done, and we know that we can produce electricity 24 hours a day, so no intermittency. And that's why it can be complementary with wind turbines and with photovoltaics. And also, some people propose, so there are many publications, more than 1,000 publications on solar chimneys. And some people proposed special devices to produce at peak hour. When you wake up, you start using more electricity from 6 to 8 in the morning, or after you finish working at the happy hours, you consume more electricity from 4 to 6 p.m. And so they have worked on the devices to store the energy during the night and produce it the morning or the peak hours when the electricity is the most expensive. So there are many possibilities with solar chimneys, and we think that they can be really complementary to the other renewable energies. And of course, photovoltaic is very cheap and the cheapest energy in countries where you have a lot of sun. But in New York or in UK, it's very expensive, and you need to produce also at night. So you have to pay for the not having intermittency. And that's why nuclear power is proposed in some countries, because there is base load production. And the solar chimneys can do that, but in hot countries.
So are you saying that solar chimneys can be used for power production in addition to methane removal, like at the same time?
Yes, in fact, that's the best.
Okay.
That's the best synergy, because there is no, as the photocatalyst can be just a small coating under the greenhouse cover, or maybe we don't have tested yet, but maybe also a second coating of photocatalyst can be on the ground. There is no pressure drop, and so the production of electricity, you have the same production. It's complementary.
I see.
You don't use the heat, and also you can also put carbon dioxide devices to carbon capture devices, but there you will have a pressure drop and you will have a less electricity production. But there are also many synergies and complementaries between solar chimneys and CDR, or direct air capture.
Yeah, and just to make sure I'm understanding this and to clarify for some of our listeners, the way the power production would happen is as the air is flowing through, it kind of spins through a turbine or some sort of device. Okay, makes sense. Yeah, that's really interesting, and I'm sure there's also other benefits like if you do this in a residential area, in like a skylight, you could have cooling for the housing or other just like thermal benefits.
Yeah, in fact, Wei show one or two pictures of images of the small-scale solar chimneys, which are used by the architects for urban ventilation. And so you have, maybe we can show again the slide. You have trombe walls, urban solar chimneys, and also the double skin walls. On buildings, which work for ventilation purposes, and the architects use this since a long time. And in fact, the initial solar chimneys were used by the Sumerians 3,000 years ago in Iran and Iraq.
Yeah. The building stuff looked really interesting, both from like an air quality standpoint in particular. So are you saying that like with this photocatalytic technology, it could act as like a drop-in replacement, like you essentially apply a coating to existing like these kinds of urban solar chimneys, and then you can offer improved air quality benefits in addition to methane removal?
I'll let you answer, Wei, or?
Yes, that's the more synergy you can apply in urban areas. The photocatalysis itself, it can not only react with methane to convert it to CO2, it can also remove air pollutions, lots of NOx, and also if on farm conditions, you can also remove ammonia. Yeah, another air polluter. So yeah, there's a synergy, not only greenhouse gas removal, but also air pollution removal.
Got it. So, Charles, were you going to ask something, or?
Go ahead.
I think so. I think the one thing I'm curious about is trying to contextualize this with carbon capture. And so at least the way I look at it, when you compare this with carbon capture and the economics of it, the two challenges are potentially the lower concentration. And also, I think the fact that methane is much shorter lived in the atmosphere and like would probably degrade in a few years. But I think the big benefit I see is you don't have to use this in isolation. You can use it with a lot of other systems versus like direct air capture devices, right, are used in isolation. So I guess like when you think about this and carbon capture, like how do the economics and importance and like how much energy we should be spending on this kind of compare between this and carbon capture?
In fact, carbon capture requires energy for the capture to move the air, and also then thermal energy to regenerate the catalyst. I mean the scrubber, the alkaline base that will suck the carbon, which is an acid. And for photocatalysis for methane, you only it's all passive. The photocatalysis is window or on the glass. It's a small coating. It can be dioxide, which is well-known photocatalyst, and the airflow is free because it's solar driven. And in fact, we don't capture after we have transformed the methane by oxidation into carbon dioxide, which is anyway the way the methane finishes in the atmosphere. This is the natural process. We only accelerate this natural process, so there is no capture. There is no need to sequestration, and all the things are passive, and it's decentralized because many of the carbon capture, and especially direct air capture, will be centralized plants, and you can do photocatalysis in a decentralized way, even if it's a small scale. But if you have all the buildings equipped with this, you can remove significant amount of methane. And of course, methane is short-lived. But right now, the oxidative capacity of the atmosphere is not enough. So the concentration in the atmosphere is increasing. And the last 2 years, 2020, 2021, that were the highest increase in atmospheric methane ever measured since the measures started. Right now, due to global warming, the wetlands are emitting more and more methane, and this is considered as biogenic, as natural, but is driven by man-made global warming, and we don't know how much more methane will be released. So we can mitigate some of the anthropogenic emissions from the agriculture or from the oil and gas, but we cannot mitigate emissions from natural water bodies.
One thing I'm curious about is in CDR, we often like to talk about dollars per ton of CO2 removed. It's like kind of the baseline comparison between different technologies. And I know this is a little different because methane has a different residence time and different global warming potential, and you're converting methane to CO2 in this case. But have you all done a preliminary calculation? What is kind of the expected dollar per ton of like equivalent CO2 removed for this technology, and how does it compare with others?
Not yet on my side. I don't know if Wei has done something like this, but yeah, it's not. It's a very early stage because, as Wei showed, the first experiments they carried, it's on a 2 meter high, 2 square meters chimney. And so for the moment it's very difficult to extrapolate, but probably much less than for carbon dioxide if you account on carbon dioxide equivalent, because on a 20 years base global warming potential, methane is 86 times more powerful than carbon dioxide. So if you account with this global warming potential, probably the cost per ton of methane will be much lower. And today is not the topic, but there are other technologies of methane removal, and there are conferences where the team working on this say that they will reach less than 10 or even less dollars per ton equivalent carbon dioxide.
Yeah, no, that's a really interesting number, but would love to see some of the math behind that published at one point. Sorry, go ahead, Harsh.
No, I was just gonna say like that. Like if you look at carbon credit markets, like that's now like one of the like what's considered a cheap credit. So if you could sell it, if you could actually do it for that much, that's really, really interesting.
Yeah, in fact, as the lifetime is much lower, between 10 and 12 years for methane in the atmosphere, the US government has been talking about $1,500 per ton of methane. They are not talking about carbon dioxide equivalent for the moment. But yeah, of course, that's already a very interesting price. And I think that with photocatalysis, that could be quite competitive.
Yeah. Do you think methane removal is, as a broader topic, is something that's gaining traction? Or because I mean, we've all heard a lot about mitigation and flare gas and all of those things, but like, I'm just curious, like, do you have any thoughts on, do you see other researchers or industry moving towards methane removal, and kind of where does it go from here?
Yeah, so I will do some advertising for a seminar who will take place 15th September with an NGO organized by an NGO, which is not for profit. The name is Methane Action. So there will be several people talking about this, and yes, in fact. Even if you succeed mitigating anthropogenic emissions of methane, there are still some hard to mitigate emissions, anthropogenic emissions from the agriculture and especially from the cows, but also from the rice paddies. You cannot mitigate 100%. And as you don't know how much methane will be emitted naturally by the wetlands, the rivers, the lakes, the ponds, and even the hydropower reservoirs, which emit a lot of methane, especially in the tropics. You cannot mitigate those. So methane removal is really complementary to mitigation, and they can work together. And we really need using both. And there is a very interesting report from the Climate and Clean Coalition and the UNEP, United Nations. It's a global methane report from last year. And they say that we will need to mitigate at least 45% of the anthropogenic emissions. And in fact, the global methane pledge that was signed at the COP26 last year only targets 30% mitigation. So we need to do more, even more than that. And the global methane pledge has so far been signed by 120 countries, but it's not legally binding. And also big emitters like Russia, China, India, Saudi Arabia have not signed it. So the mitigation is, we have to have very aggressive mitigation methods and policies, but also methane removal is complementary and will be needed.
It's fascinating.
Wei, one thing I was wondering if you could share a little bit about, to the extent that you're able, like what is kind of the composition of the photocatalyst? How is its like, have you looked at its stability? So I know photocatalytic stability is another issue, though maybe in air it might be better. And what's, are there any raw materials or like challenges with scaling up processing? Yeah, anything you want to share on that topic?
I will let Wei Li to answer.
Yeah. At the moment, for the data I've shown, so they are all measured with very cheap, commercially available TiO2, titanium dioxide photocatalyst. So yeah, there are, in the area of photocatalysis research, so there are very quick progress in this field. You can find different kinds of new materials reported every day, and we can track this progress to try to find if these new materials can perform better than TiO2 or not. So this is one part of our research. And also the duration, stability. Yeah, this is a big part of our research too. So at the moment, for the TiO2, we also need to consider the air we are processing. It's not only methane is there. As I said, we also the air pollutes, and very simply just the humidity, the water vapor in the air, it can all react with the photocatalytic material. So they can all affect the durability of the photocatalyst. So yeah, we do need some good research in this area to monitor how durable the materials will be. But the early indication that is that at least for the commercially available TiO2 material, so they are quite stable during the tests we have done.
One thing I'd be really curious to hear about that, you kind of inspired me based on what you were sharing earlier, Wei, about your 2-meter prototype that you just put in your lab. Is like what, you know, with OpenAir's community of like open source activists and like researchers, you know, a 2 square meter prototype, that's like something that can fit on like someone's driveway or someone's backyard porch. I'm curious, could you share like what is roughly like the cost of that? And like, yeah, it'd be really interesting to see like if people could like deploy these mini prototypes in a distributed way, and that way people can kind of do these field measurements for you, like different humidities, different surfaces, and like help scale down the cost as well. I'm curious, like, yeah, what is roughly the cost we're talking here? Like $1,000, $10,000?
No, less. It's very cheap. It's like another layer of window. So that's it. It's very cheap, simple structure, cheaper material. So like another additional layer of window. So if at the moment we only set up a prototype, it's already very cheap. You can imagine if we can give it a massive production, so then the cost can be even lower.
Yeah, it'd be really cool to see if you could open source your design. Like like I guess you say it's basically a fancy window, right? It's just has like a cone at the top and a flatter base, and then you just need the TiO2 coating, and maybe like some air measurements of whatever's coming out from the bottom and whatever's coming out from the top. But yeah, that'd be really interesting to see, since it is so, like you say, cheap and deployable. Maybe something to talk about further after this.
To give a complementary information about the stability, in fact, you have heard about self-cleaning glass.
Yeah.
And this is having a coating of titanium dioxide. And we are partnership with the biggest producer of self-cleaning glass. And some studies have been done. And nearly 10 years after the window was installed, they tested it again, and it was still active.
I see. Wow, that's very cool.
So it was not tested on methane removal. It was tested on cleaning the oily, sticky pollution.
So slightly easier condition.
Your car.
Yeah, I see. Wow.
Awesome.
I guess on that note, since I guess I already brought it up, you know, OpenAir, you know, we're a collective of policy advocates, open source researchers, and designers. I guess I already threw something out there, but I'd be curious to hear from both of you. You know, are there any other ways that you think the OpenAir community can help you along with your research and your development of this idea?
Yeah, in fact, Wei also showed the trombe walls. And this is inside your home. You can warm your home in winter and store it for the winter and during the day in winter. And you can make ventilation during the day. But there are maybe 10 publications of 2 different teams working on removal of pollution inside your home, especially the pollution due to your furniture, which is formaldehyde. And some other volatile organic compounds inside indoors, and so they are using the same. Solar chimney effect and photocatalyst on the window, on the glass, so I think open source is a very good idea because many people can try and reduce their pollution and their indoors pollution and also test for methane outside.
That's fascinating. We will, once you have the product ready, we'll have to ship it out to all our members, then have them collect data and send it back to you. Awesome. I think with that, really appreciate both of you taking the time. This was fascinating. I think all our members would really, really enjoy the episode. Thank you.
Thank you to you both.
Thank you for organizing this. Thank you.
Awesome.